Okay, so this is for chapter 10. We'll start with 10.1. So the first example here is just sort of playing around with the main formula for density. Rho for density equals mass divided by volume. Okay, so this problem says what is the mass of a solid iron wrecking ball of radius 18 centimeters. Okay, so we're into this chapter where now we're talking about um, substances, so solids, liquids, gases. So the fact that this is iron, okay, is important. So first, we're actually asked to find the mass here, right? So you'll see a lot of problems where you gotta solve for one of the other two, mass or volume. Um, so mass is density times volume, so density of iron, and we'll just look that up on page 261. So iron or steel have the same density. Okay, so 7.8 times 10 to the third, and this is in kilograms per meters cubed. So think about that number, 7,800 kilograms is a lot, but a meters cubed is a pretty big. Imagine a block of iron a meter on a side, and that's how much mass it would have. Okay, then we have to deal with the volume. So this is a sphere. So we need to know this. Usually sphere and cylinder and cube volume formulas. This is in meters cubed, so we need this radius in meters. Um, and in the interest of saving time, I'm not gonna plug in all the numbers because at this point you just do this calculation, multiply, plug it in here and multiply by that, so you can get the answer you need. So I think we're okay with doing that. Okay, 10.2. So now we're moving on to pressure. So the general formula for pressures. Pressure is force divided by area. Example 10.2, we have a 60 kilogram person's 2 feet cover an area of 500 square centimeters. Part A, determine the pressure exerted by the 2 feet on the ground. And B, if the person stands on 1 foot, what will be the pressure? So what's the different pressure there? Um, well, we need to look for what force is involved here, and this is a person standing on the ground, so we know the force is the weight, which is mass times g. And I mean, these first two examples are really straightforward. The only thing we have to worry about here is the area, because if it's mass per area, then in terms of units, this is going to be newtons per. I remember we're always trying to use meters, so newtons per square meter. Sometimes, in fact, the homework I think prefers pascals as the unit. Let me try to focus this here. Okay. So we just have to convert. The only thing I want to show you here is when you're converting this, it's a square unit, so you're going to go like 1 meter per 100 centimeters, but you got to square this. Okay. So calculate the force, do this conversion, and then just divide. Okay. Now, for part B, it's the same process except we assume the feet are the same size, so it's half the area. And you can see if you half the area, then the pressure will double because it's inverse like that. So whatever you get here, the answer to the second part would be double whatever you get for part A. Okay. 10.3. Now pressure we can sort of extend beyond just objects in contact. Okay, like was the first example here. So pressure in a fluid we're dealing with. Now this is a static, for the most part, fluid. Okay. at a depth. So this is H. I know that's height, but it also stands for depth below a surface of a fluid. Um, Usually we're talking about water. So for 10.3 we have pressure at a faucet. The surface, we have a water storage tank 30 meters above a kitchen faucet. Okay, so you can see, I'm going to draw it here. Here's the water tank. The pipe goes down like this and then back up, and here's the faucet right there in this height here. Now, it turns out it doesn't matter what the pipe does, so it doesn't matter that it goes down and back up. So pressure depends on height. So say at this little section, let's say here's the height of the faucet. So the pressure here is going to be the same as the pressure on the other side. And the pressure here is the same as the pressure here. Okay, so whatever loops, as long as it works. Okay, as long as you don't try to go back up above, the original water tank. And so again, we have, I'll mention here, the density of water is actually defined. Actually chose, back when they were coming up with units, I don't want to digress too much, but they chose these units so that it would be 1,000. Okay, we all know G is 9.8, and so IH, and just plug in your 30 meters there. Okay, let's see, we got 10.7. Next, so we're moving into Archimedes' principle and buoyant force. So this is using, I'm not going to go into the whole background of this, but the buoyant force, so an object in a fluid, that can be water, it could be, there's a homework problem where it's mercury, air also works as a fluid. Okay, so we're going to have density of the fluid times G times the volume of the object. Okay, so a trap here is, this is not the density of the object, this is the volume of the object, but density of the fluid. Okay, now technically this is the volume of the object that's submerged. So for a fully submerged object, that's just equal to the object volume. There could be some problems where the object is not fully submerged, but you need a way to figure out, how to calculate what, they need to tell you a percentage or something like that. Okay, so 10.7. So we have, let's see, 70 kilogram statue. That's the object. With the mass, we have the volume. And I'll say one more thing about volumes is when you do problems with volume in meters cubed, the numbers can be very small because a normal, like, say, handheld sized object is going to be like 10 to the negative fourth, 10 to the negative fifth meters cubed. So a lot of times it will be given in centimeters cubed, just to have better numbers, but we still have to convert this because G, if we use 9.8, that's in meters, and if we want the answer in newtons, we have to convert this. So we'll do that first. Well, now it's cubed, right? So we got to cube this. So actually dividing by 1,000,000, or 10 to the negative 6. Let's see, dividing by 10 to the 6, so that's, now this is a pretty big statue. Okay, so what do we want to know? How much force is needed to lift it? Okay, so in a lot of problems, the fully submerged object and the forces, gravity down, buoyant force up. Now, in order to lift this statue, basically you just have to barely apply a buoyant force that's equal in the upward direction to the gravitational force. Okay, so you have to interpret that. We mean, what buoyant force? Let me read this again. Sometimes I get a little bit ahead of myself. Okay, so I did. So in order to lift this, then these two are going to be set by basically the mass and the volume of the object and what fluid it's in. So we want to apply now a third force, an applied force that's going to be our lifting force. Okay. But now we want to apply this equilibrium, meaning what force do we have to apply just so that the two upper forces cancel out the down force? Okay, putting the right positives and negatives. Okay, and we'll get to this where it's going to be the difference between the gravitational force and the buoyant force. Okay, so mg minus what we have up here, rho f gv naught. Just plug everything in and get an answer now. Okay, so now we need 10.8. Okay, this is another type of Archimedes problem. So basically, I'm sorry, this is the Archimedes. That previous one, the statue was of Archimedes, but it was just a buoyant force problem. Okay, Archimedes is specifically where we're taking sort of an unknown density, an object of unknown density. I'll draw it here, and we're going to weigh. So let's put this on a scale, a little handheld spring scale. Okay, and this is going to give us a weight in air, and then we're going to take this scale and submerge it in our water. Now with a buoyant force pointing upward, okay, this will give us a different weight. Call it weight W prime, meaning for the weight in the fluid, and this should be less than this. So the scale reading here is less than the scale reading there. Okay, and we get down to basically what Archimedes' principle says is that the difference in the scale readings is equal to the weight of the displaced water. And I'm not going to go through the whole derivation here, but we get down, and this is a place where you can start. So density of object over density of fluid is equal to the weight over the weight minus the weight in the fluid. Now, a little shortcut here is, what is the weight? Well, it's m times g, right? So we can write it like this. And I'm going to use m prime g. And the g's cancel. Okay, so in other words, you can go directly into the calculations with the masses or the weights, depending on what the problem gives you. So this problem gives us masses, right? So it says when a crown of mass, okay, so it's telling us the crown has a mass in air and a mass in water. So that's our m prime. Is the crown made of gold? Really, that's telling us to find the density. Okay, so taking from here, we want to find rho object. This is going to be rho fluid times this fraction here. And of course, rho fluid here is water, so that's 1,000, and then times that. And the story is that, this is how Archimedes discovered this, and the crown in this example is not gold. So we found the density and then compared it to a list of densities, and it doesn't match. Okay, 1010. So now this is another Archimedes type problem, but it's a little bit different. So basically we have helium balloon, and it has a load attached to it. It says what volume of helium is needed to lift a 180 kilogram load. So this is very similar to that first problem, except now it's a helium balloon in air. So in this case, the air is the fluid. The helium is actually the object. Helium contained in the balloon is the object. Okay, so we have, let's see, we have up is the buoyant force. We have down here is, I'll write it over here, Fg of the helium itself. We have to consider the helium's own mass, just like this is an object. So it's Fg of helium, and I'm considering this all one single object here. And then we have the F, I'll just call it Fg, which is the weight of the load. Okay, and again, it's one of those situations where, say, if the sum of the forces equals 0, it will just barely lift it. B is up and the two gravities are down. Now we want to find volume of helium, right? So that's going to come in FB. So if I plug everything in here, so I'm going to have rho air G volume of the object, which we're not considering the actual mass of the balloon material, just the helium itself. Okay. And I'll go ahead and solve this for this over here, but this is going to be M of helium G plus just the mass of the load G. First we can see all the G's cancel. That's good. So volume of helium, mass of helium, mass of load over density of air. Now, let me think about this for a second. Okay. Yeah, that's right. And you might think, okay, we don't have, get on a new page here, we don't have the mass of helium directly, right? So you find a lot of times where you have to go back to the density equation and see if you have the other two variables, and then you can calculate the third one. So we don't have the mass of helium from the problem, but we have the density of helium, and volume of helium is our unknown. So we'll plug this in for mass of helium. I'm going to leave this over here for now. You'll see why in a second. Because I have to solve for volume of helium, so I have to get this on the other side. So just real quickly. Because these kind of things happen a lot in physics equations where you have the variable you're solving for in two different, and it just takes some algebra manipulation. So just moving this to the other side and then factor out the VHE. And there we've got, one more step, and we're solved for VHE here. Okay, now that'll give us our final answer. We just plug in 180 and then the 1.29 and the 0.179 here, and we'll get us our answer. Okay, what was that? Okay, I got one more here. This is 1014. Now that right there, what we've done so far is basically the bulk of the problems. But there's another, that stuff is all considered basically statics. Okay, if you've ever heard hydrostatics. But now the second part here is hydrodynamics, or fluid dynamics, meaning what about if, basically if the fluids are actually moving. Um, First thing I'll mention, I'm not going to do the example because I don't think it's a good example, but the problems are very straightforward with, sorry, when you have a tube and it changes diameter or radius. So here's R1, here's R2, way off the page. Okay, so if we go from left to right or right to left, the radius is changing, so that cross-sectional area, if these are circles, here is changing. And if I have V1 here, that means V2 is going to change. If you make the pipe smaller, the speed's going to increase. But you can't have any gaps. So you can't move the same volume through. I'm sorry, you have to move the same volume per time through, okay, this section and this section. So the speed has to change. And that's called the continuity equation. And it's pretty straightforward. A1 V1 equals A2 V2. So any problem where diameter of a pipe or something is changing, you'll have three of these and calculate for a change in speed. Okay, but for this last one, this is not 1014, but for 1014, now we're going to use what's called Bernoulli's equation, where you have these two. It's kind of like this, but an extension. So basically, for Bernoulli's, you can have, I'll just kind of draw an example, a pipe here, and then it can narrow or get bigger, and also it can change height. So you can have something like this, where it actually comes down, gets smaller, and changes height. Okay, so everything, and for some reason, I don't know why they do this, they have two first and 1 second. It doesn't matter. It's completely reversible. You just have to keep track of which point is 1 and which point is 2. I'm just going to stay with the book here. So from 2 to 1, the pressure inside the water is changing. We basically have Y2 and Y1, so the height is changing. And we have V2 up here and V1, which are changing. The density is constant throughout. So Bernoulli's, and it looks like a really terrible, complicated equation, and it kind of is, but you can usually simplify it. This actually comes from, some of the terms might look familiar. This comes from the conservation of energy equation. Except with densities. So, 1. So that looks like a kinetic energy term, except with density instead of mass, and that looks like a potential energy term, again, except with density instead of mass. Okay, now example 1014. So, water circulates throughout a house in a hot water heating system if the water is pumped at a speed of 0.50 meters per second through a 4 centimeter diameter pipe in the basement under a pressure of 3 atmospheres. What will be the flow speed and pressure in a 2.6 centimeter diameter pipe on the second floor 5 meters above? So we have a situation where, let's see, so our pipe is getting smaller. So it's kind of like this. I'll draw a picture. It's kind of like this. Here's our pipe, and then it comes up and gets bigger. So 0.2 and 0.1. Now let's see what we know. And just keep in mind, 0.2 is basement and 0.1 is upstairs. So upstairs we have V1. We have area, and this is a diameter and it's in centimeters. So let's see, area is going to be pi radius squared, and you'll get some value there. Let's see, what else do we need? Do we need pressure 1? Yes, pressure 1 is 3 atmospheres. We're going to need to convert this to pascals. So times 1 to the 5th pascals per atmospheres. You actually know all three things, right? Pressure, speed, height. And I just did this all backwards. That's all basement stuff. Change this all to 2's. Okay, now for upstairs. So we know A2 is and you'll calculate that. Now it's 5 meters above, right? So with Y1 and Y2, now Y2 is lower, so we can say Y2 is 0. You can always do that. So this whole term is 0. And Y1 is 5 meters. I tell you that 2 and 1 actually gets, it's hard to keep track of what's what here. This needs to be A1, right? That's area 1. Now we don't know speed 1, and we want to know speed 1 and pressure 1. Okay. So if you look at the equation, if we don't know speed 1 and pressure 1, even with this term being 0, that's 2 unknowns. So we need a second equation. So you can always use the continuity equation no matter what is happening to the pipe or the pressures. This is always true for any situation. And so we set this up, and we know area. Let me get this off there. Put this all on one screen. We know area 2, we know area 1, we know V2. Okay, so first step is calculating V1 with the continuity equation. And we're pretty much done here. I'm not going to go through all the calculations, but this is the steps. And then once you have V1, now the only unknown here is P1. So solve this for P1, and there's a lot of little calculations to do, but that'll get you the answer. Okay, so I think that's good. So we'll go ahead and stop there.